The physical scenarios we have explored so far involve a quantum particle undergoing bounded motion. For example, in the case of a harmonic oscillator, the particle's motion is confined by the restoring force of a spring. Similarly, in the particle in a box scenario, the particle is restricted to a finite spatial interval by two impenetrable walls. While understanding bounded motion is important, many physical phenomena involve quantum particles in effectively unbounded motion. The remainder of this course will focus on unbounded systems. The simplest physical system exhibiting unbounded motion is a free particle. Let's develop its quantum mechanical description. Let's consider a one-dimensional space, represented by the x-axis, with a particle of mass m. No external forces act on the particle, allowing it to move freely along the x-axis. The time-independent Schrödinger equation for this system has the following form. The equation determines the function lowercase psi, and the corresponding energy E. Defining k, such that E equals h bar squared, times k squared over 2m. We can rewrite our Schrödinger equation in this form. Previously, when we encountered this equation, we wrote its general solution as a linear combination of cosine and sine functions. Now it will be more convenient to express the solution as a linear combination of two complex exponentials, e to the power of ikx, and e to the power of minus ikx. A and b here are arbitrary constants. Notice that solutions of this form exist for all positive energies E. This highlights an important difference between bounded systems, such as a particle in a box, and unbounded systems, like the one we are considering here. In a particle in a box system, the energy is quantized, meaning the allowed energies form a discrete set or spectrum. In contrast, the energy spectrum of a free particle is continuous and includes all positive values of E. Now, the general state of the particle is a superposition of all possible solutions of the time-independent Schrödinger equation, for all values E, or k. Each function contributing to the superposition takes the form of lowercase psi, multiplied by the usual complex exponential of time. Previously, in the case of bounded systems, we expressed such superpositions as a sum over all allowed energy values. In the unbounded case, however, the allowed energy values form a continuous spectrum, meaning that the sum must be replaced by an integral. Thus, the general wave function, psi of x and t, will be given by an integral over k, with the integration domain ranging from 0 to infinity. But what is the function that appears under the integral sign? It is the lowercase psi times the complex exponential of time. The function psi involves two arbitrary constants, a and b, for every value of k. These constants can be conveniently accounted for using a single function phi of k. To achieve this, let's define a as the value of phi at k, divided by the square root of 2 pi. Similarly, let b be the value of phi at negative k, also divided by the square root of 2 pi. Do not be confused by the factor of 1 over the square root of 2 pi, it is purely a convention. This factor has no conceptual significance and is introduced solely for convenience. Equipped with the function phi of k, we write the function lowercase psi in the following way. Finally, we multiply psi of x by the complex exponential, explicitly expressing energy E in terms of k. This completes the expression for the general spacetime dependent wave function of a free particle. Notice that this expression can be significantly simplified. By expanding the curly brackets, we obtain two integrals. One involving the function phi of k, and the other involving the function phi of minus k. By changing the integration variable from k to minus k in the second integral, and then combining it with the first integral, we arrive at the following result. The expression we have obtained gives the most general quantum state of a free particle. The complex-valued function phi of k, in this expression, serves as a parameter that completely defines the state. While this function is essentially arbitrary, it must satisfy the condition that the particle's wave function derived from it is normalized to unity. As an example, let's consider the scenario of a free particle Gaussian wave packet. To this end, let's take phi of k to be a real-valued Gaussian function. There are two real parameters here, p and sigma. As you will see by going through the exercises for this lesson, p represents the mean momentum of the particle, and sigma controls its position uncertainty. By substituting this Gaussian function into the integral on the left, and calculating the integral, you will obtain the following spacetime dependent wave function. Here, alpha is a linear, complex-valued function of time. As you work through the accompanying exercises, you will also verify that the wave function, psi of x and t, is properly normalized. Let's visualize this wave function. At time t equal to 0, both psi and the corresponding probability density, given by the squared modulus of psi, are real-valued Gaussian packets, centered at 0. Here is the plot of the probability density. Now, let's set the time ticking, and observe how the probability density packet evolves over time. In this example, with p set to a positive value, you can observe that the wave packet moves to the right, with a constant average velocity. Additionally, its width, or the particle's position uncertainty, increases over time.